This lesson is diagonalize the matrix, and here you have two form. Both of these form are the same thing, it's just rewritten in a different way. Okay, so here I have A, P, D inverse of P, which is also the same as AP equal PD. All you have to do is just take this inverse, write it over here, and then you have AP equal PD. Again, these two form are the same thing, it's just rewritten in different form. So here I have a matrix A. Now I need this matrix A to subtract by the lambda times identity. Since this is a 2 by 2, you also have a 2 by 2 identity times with lambda. So now we just have to multiply. So this is my identity 1001. So multiply the lambda to this identity. So you have lambda 0, 0, lambda. Take the A, subtract from it. So 2 subtract lambda, 3 subtract 0, 4 subtract 0, 1 subtract lambda. Next, we will take this matrix, find the determinant of it. So find the determinant of A minus lambda times I, which is this right here. So since this is a 2 by 2, A times D, which is here, minus 3 times 4, which is here. Now just multiply it out. 2 times 1 is 2. 2 times lambda is negative 2 lambda. Negative lambda times 1 is this negative lambda. Negative and negative gives me this positive lambda squared minus 12. Rewrite it in highest order form. So I have lambda squared, 1 negative 2 lambda, 1 lambda, so that gives me negative 3 lambda. 2 subtract 12 gives me 10. Factor out the characteristic polynomial. If you remember from the last lesson, this is called the characteristic polynomial. Factor it out, solve for lambda. My eigenvalue is 5 and negative 2. Okay, now take this eigenvalue to go find the basis or vector that belong to each of these eigenvalue. Okay, so your next step is to find the basis or the vectors that belong to each of these eigenvalue. So for the first one, is 5. So go back and put the 5 in. So instead of lambda up here, as you can see up here, right here where it says A minus lambda I, instead of lambda, you put the 5 in. Okay, so instead of lambda, you would put 5 in. Okay, so I have here A minus 5I. So again, instead of lambda, you put 5 in. So there's my A, and I is the 1001. So times 5 to it. And then after that, you just subtract. So that gives me add or subtract right across. So that gives me negative 3, 3, 4, and negative 4. Now after that, use this matrix to do row operations or row reducing to get my basis or vector that correspond to lambda equal 5. Okay, so this is negative 3. So use this matrix right here to do row operation to get my basis or vector that correspond to the lambda equal 5. So this is negative 3. I need it to be a 1. So multiply the reciprocal, but put another negative in because I need a positive. So negative 1/3 times negative 3 gives me 1. Positive 1. Negative 1/3 times 3 gives me negative 1. Next, I need this 4 to be a 1 as well. so it makes it a little bit easier. So multiply by 1/4. So 1/4 times 4 gives me 1. 1/4 times -4 gives me this -1. I need this to be a 0. So multiply by the opposite, which is -1. So -1 times 1 is -1 plus 1 gives me this 0. -1 times -1 gives me +1. Subtract 1 gives me this 0. Now, as you can see, this is my pivot, and this is also my pivot. Since this is the only one that has a pivot, so we will write x1 minus x2 equal 0. This is my second pivot, which is x2. However, there's a 0 here, so x2 is free. Okay, now we write all of the value for x2. So as you can see, I have x2, x2. So first position or first value of x2 is this one. Second value of x2, which is this one, since it is free, 1. Okay, now we can write this as v1, 1, 1. So if you use this format or this format, it is the same thing. Okay, so this vector or basis is corresponding to this eigenvalue, which is lambda 5. Now repeat that whole process again for lambda -2. Okay, so here's the -2 down here. So -2, instead of using lambda, we put -2 in. However, there's a negative and negative, so become positive. Okay, and this is my 1, 0, 0, 1. So +2 times that gives me 2, 0, 0, 2. And then just add across, that gives me 4, 4, 3, 3. So this matrix, use this matrix to do row operation or row reducing to get my second vector or basis that correspond to lambda -2. Okay, so lambda -2. So using this matrix here, so we need a 1 here and also a 1 here, so it makes it easy. So multiply 1/4. So 1/4 times 4 gives me 1. 1/4 times 3 gives me 3/4. 1/4 times 4 is also 1. 1/4 times 3 is 3/4. I need this to be a 0. So multiply by -1. -1 times 1 is -1 plus 1 gives me this 0. -1 times 3/4 is -3/4 plus 3/4 also 0. Now since this is a 0, we can stop. Or if this is a 1, that's fine too. But since this is a 0, we can stop. So 1 x1 plus 3/4 x2. Okay, solve for it. I get -3/4. This is my second pivot. However, this second pivot is a 0. So x2 is free. Okay, now put these in its vector. Okay, so this is my first term of x2, which is -3/4. This is the second term of x2, which is this one. Since it is free, always 1. Now I don't want the fractions, so multiply by the denominator, which is 4. So multiply the 4 will gives me -3. Multiply the 4 gives me 4. So our second vector, which is this, that correspond to lambda -2. Okay, so going back, this is the first vector that belongs to lambda 5. This is the second vector which belong to lambda -2. Put these two bases together, which will give me my P matrix. One more time, put these two vectors or bases together, which will give me my P matrix. So my P matrix is all of the bases or vectors to the eigenspace. The D is the matrix that belongs only to the eigenvalue. One more time, P matrix is all of the bases that belong to the eigenspace. The D matrix is only eigenvalue. So here's the eigenvalue 5, here's the eigenvalue -2. These two is just 0. Okay, next I want to check if this is true or false. So I'm going to check AP equal PD, which I have in front, which I have from the top right here. AP equal PD. Are they the same? So I have A, which is the original. P is the vector or the basis that belong to the eigenvalue. Now we just multiply across. So row times the diagonal. Row times the diagonal. So 2 times 1 is 2 plus 3 times 1 is 3. So 2 plus 3 gives me this 5. Row to this column. So 2 times 3 is -6. 3 times 4 is 12. -6 plus 12 gives me this 6. Okay, repeat that to the bottom. So 4, 1 times this. So 4 times 1 is 4. 1 times 1 is 1. 4 plus 1 gives me 5. 4 times 3 is -12. 1 times 4 is 4. -12 plus 4 gives me this -8. Now do that again for PD. P is the basis or the vector belongs to the eigenvalue. This is the D matrix that only has the eigenvalues. So just multiply across. 1 times 5 is 5. -3 times 0 is 0. So just 5. 1 times 0 is 0. 3. -3 times 2 gives me this this +6. So -3 times -2 gives me this 6. Next, 1 times 4. This row times this column. So 1 times 5 is 5. 4 times 0 is 0. 5 plus 0 is this 5. This row, this column, 1 times 0 is 0. 4 times -2, -8. As you can see, since they are the same, okay? So they are the same, and because they are the same, we can get our inverse, okay? Since they are the same, we can get our inverse. So to get the inverse, we will use the P matrix. To get the inverse, we need the P matrix, okay? Using the P matrix. So find the determinant of P. So 1 times 4 is 4 minus 3. -3 times 1 is -3, but I have 2 negatives, so that gives me positives. 4 plus 3 gives me 7. Using the determinant, using the inverse formula for 2 by 2, the AD switch, -B, -C. So AD switch. So 4 go here, 1 go here. That's what I have here. The 3 extra negative, so become positive, extra negative, -1. Now all we have to do is just bring along this 1, 7 to this matrix. Okay, so this is our inverse matrix, okay, of P. One more time, this is the inverse matrix of P. Okay, now we want to check is A equal PD P inverse. Just what we have in the front on the top right here. A equal PD minus, A equal P times D times P inverse. So again, these two should be the same. Okay, just rewritten in different order. Okay, so check is A equal PD times the P inverse. Now PD, we already have PD, which is up here. We already have PD, which is up here. Here's my PD. Okay, again, we already have PD, which is right here. So bring this matrix down here, and then the P inverse, this is my P inverse, put it here. Now all we have to do is just multiply. So this right here is our PD matrix. Again, where did I get this matrix? Which is up here. This is my PD, okay? My P inverse is here, okay? Now put those two together and then multiply. So let's take this matrix, leave that alone first. And let's move this 7 over. So multiply the 1 7 to all this. So it becomes 4 7, 3 7, negative 1 7, and 1 7. And then after that, take this matrix times this matrix. So row times column, row times column. So 5 times 4 is 20. 6 times negative 1 is negative 6. Okay. This row times this column. So 5 times 3 is 15. 6 times 1 is 6. And then this row times this column. So 5 times 4 is 20. Negative 8 times negative 1 is positive 8. This row times this column. 5 times 3 is 15. Negative 8 times 1 is negative 8. Now simplify a little more. 20 subtract 6. That gives me 14. 14 divided by 14 divided by 7, 2. 15 plus 6 is 21. 21 divided by 7 gives me this 3. 20 plus 8 is 28. Divided by 7 gives me 4. 15 subtract 8 is 7. 7 divided by 7 is 1. And as you can see, when we multiply this, it comes back to the original matrix that we have, okay? So when we multiply this, it comes back to the original matrix, which is 2, 3, 4, 1. So one more time. Diagonalize the matrix. We have two different forms, but they are the same thing. Okay, it is written in a different format, but it's the same thing. This is the original matrix. This right here is your characteristic polynomial. These are your eigenvalue. Use the eigenvalue to find the vector or the basis to the eigenvalue. Okay, so this basis belongs to this 5. This basis belongs to this negative 2. Okay, this negative 2. Put these two vectors or bases together. That will form my P. P is all of the bases that we found from the eigenvalue. One more time. P is the basis or the vectors that is according to each of the eigenvalues, okay? And then the matrix D is only the eigenvalue. D, the matrix D is only the eigenvalue, okay? And then after that, we will check, are they true or false? So AP, P times D, since they are the same, we are good to go that they are true. Now after that, find the matrix inverse, the inverse matrix of P. Find the inverse matrix of P. Again, P are the basis or vectors from the eigenvalue, okay? So find the inverse of P, which we have here. And then after that, check if it's true that it does come back to the original matrix. PD, we already have it from up here. So here's my PD. So use this matrix right here and use this matrix down here. And then put the inverse matrix of P here. Multiply row and column and add, simplify, and then it will come out to the original matrix.